Good morning. As she said, my name's Emily Stoller. I'm really happy to be here. Designing materials for a living planet is one of my favorite subjects, but everyone I know has heard me talk about it already, so I love getting out and telling people who haven't already heard my shtick. So, I'm coming from the Wyss Institute, as she said, and prior to that, the majority of my career has been in industry in sustainable product development. My background is in chemistry and materials. And I designed this talk. I'll tell you a little bit about the Wyss Institute, and then I designed this talk a little bit around the chronology of how I ended up going from being a chemist to just a bio fangirl. And I think it's the direction things are going in, and I have a lot of hope that we're going to be able to do some really interesting work in the next few years around the materials. Um, so the Wyss Institute is, our full name is the Wyss Institute for Biologically Inspired Engineering, and we're a nonprofit organization that operates within the Harvard ecosystem. So we were founded in 2009 by Hans-Jörg Wyss, and the idea then in 2009 was an unusual one. How are we going to intentionally translate technology out of the academic labs and into industry in as either startup companies or licensing technologies? We have a multidisciplinary team, and everybody says that. But this isn't just what I like about it, what I appreciate about the Wyss is that this isn't just that we have electrical engineers, mechanical engineers, chemists, biologists, and we do physicians, etc. But we also have a business development team that works with us very early on to start looking at them in the marketplace. We start speaking to key opinion leaders really early on. We recognize and know what our performance indicators will be almost before we've gotten started. So I like that because it gives us some rails to work within. And then we also have in-house counsel. So we're thinking about IP and we're thinking about operating space, and that's really useful. And then we also have, and I'm biased in this way, but we have ATDs, Advanced Technology team members. And I'm one of them. And we have about 70 plus people who have been in industry and are now coming into the academic space to really help foster these ideas down the pipeline in a way that makes them sturdy when they get out into the real world. And I think that was a driver for a lot of us, that we knew there were these wonderful ideas sitting on benches that needed to move faster, especially in the climate space. So this on this side, this is sort of some of the stock material they give me that I'm supposed to tell you all. So on this side here, you can see some of the capacities that we have: synthetic biology, we have diagnostics capacities, cellular devices, and then we're using those. We've identified 6 grand challenges. Now, we're not limited to these, but this gives you a sense of where we're thinking and where we're putting a lot of our resources around brain health, infectious disease, women's health, healthy aging, cancer solutions, and my personal favorite, sustainable futures. So this is the stock sustainable future slide. We don't need to read it. It's sort of our mission, and it includes a particularly unattractive picture of me looking at plants from the back. And the thing that I think is worth thinking about for this slide is that the Wyss was about 90% healthcare focused and only about 10% in the sustainability space. And what was driving picking up this as a grand challenge is the recognition that it is somewhat absurd to think we can have healthy humans on an unhealthy planet. Our health is so inextricably linked to water, to the health of plants, to the health of our soil, to the health of our air. And we need to engineer sustainable technologies that take that into account, that recognize that relationship from the get-go. And so I've been lucky enough to build the Sustainable Futures Initiative alongside Pam Silver, who's a professor at the Harvard Medical School, and she's kind of a driving force in synthetic biology. And so I was coming from, before the Wyss, I was a director of chemistry at Zymergen, and Zymergen is a biomanufacturing company. And my background is a lot of synthesis, so I've made a lot of molecules, and I've done a lot of what it takes to, put things together. And sure, I've thought about atom economy, and I've thought about not including chlorinated solvents and all those things, but it is nothing compared to what biology can do in terms of 30 degrees C in water, these complex structures. It was amazing. So as I was leaving Zymergen, I was like, what can I do? How can I want to see this out in the world even more. So I was really excited to work with Pam. In terms of our initiative, it's really hard to bucket something so broad. So, roughly speaking, we're trying to remediate the messes we've made, foster resilience to the current and coming climate changes, and create new ways to access the goods and resources we want. And that's my personal baby, because that's what I think we can do better at. I think one of the things to think about, and so I was reading Robin Wall Kimmerer's Braiding Sweetgrass, and she's an ecologist up at SUNY. And she was describing giving her graduate level, nearly graduated ecology students a survey. And she was asking them to describe their confidence level in the negative impact humans are having on the environment. Absolutely. Everybody's 100% confident they can describe that. And then she asked them to describe a positive relationship. And it was crickets. No one can come up with what that should even look like. And I thought that was really striking because if we can't picture it, if we can't even imagine what it looks like, then I don't see how we can possibly create it. So I think a lot of how we approach sustainability and materials design starts with this unspoken assumption about our relationship to our environment, whether we are outside trying to control it or whether we're a part of it. And I think we tend towards a mastery approach. We design for things to control, we assume the systems will accommodate us, but we're putting them into a very large biological system. Biology doesn't do that. They respond, they adapt, they push back. So maybe the question isn't how do we better control our systems, but more how do we better integrate ourselves into the biological system we occupy. So being a little bit more concrete, when we think about designing for control, when we're thinking about mastery, we're thinking about designing for control. We're building things to persist well beyond their product life. And we're building them in sort of an environment where we're detaching them from the system. We aren't recognizing where these things are going to be, where they are going to operate and how they're going to interact. And I have a couple of examples for each of these after this. So I think when we're designing for control, I think we can think about designing actually more to foster an outcome. Things about how we can recognize that there is an active system and can we just get over the activation barrier and move ourselves towards product. And the other thing to think about is when we're building for persistence, that's not what nature does. Nature takes benign materials, and then those benign materials are so well designed that they work the way we want them to, and then they can be returned back into the environment. And the last thing is this idea of being able to integrate them into existing systems. So, and I like to think, we're not a scourge on the planet. We're meant to be here. We're just deeply out of equilibrium. And so I think we can think about how we create these materials with a sense of our own belonging. So one of the examples I brought up, this is part of this is actually work I did before I was at Wyss, and it's more along the lines of the chronology of how I got here and why I think this matters. So I was asked to develop a non-toxic hair dye because hair dye depends on PPD. That's been associated with bladder cancers, breast cancers, and a variety of other sort of more immediate health effects, rashes, allergic reactions. And so I was tasked with this, and they said, here, they gave me, the lead of the project gave me a bottle of melanin that came from squid. And I was like, oh, this is Mason black. That could be a good pigment. And then my job was to tear it apart and then put it back together again into the hair, or to get it to stick to the hair. And that didn't make a lot of sense to me. And I thought maybe we could look at the biosynthesis of eumelanin instead. This is the molecules responsible for dyeing our hair from blonde to brown to black, so it covers a whole lot. Red is like pheomelanin and involves sulfur, so we decided to set that aside and just focus on this one. And so the other thing that was interesting is that instead of starting with tyrosine, we could move to starting with levodopa, and then the rest of this is just an oxidation cycle that we can tip off. And so we developed a hair dye. We did it two different ways. We developed a hair dye that you could create the oxidized levodopa into a melanin pigment, stuck to the outside of the hair. That was fine. But to get even more stability, we were able to, and we did not invent oxidative hair dyes, this is how they work, but you can raise the cuticles, put your levodopa inside, and then oxidize and create a pigment. And what was really interesting is that it templated onto the existing color. So we were returning people's hair to their original color. So this is a product that's out on the market now called Hairprint. And I think it was really interesting because I thought, wow, we really need to recognize how biology does things. Another thing, and when we're thinking about persistence, the big one right now, the big bugaboo is PFAS. We've accepted this sort of persistence as a cost of the performance we want. And they're incredibly effective. They have low surface energy, but they're through highly persistent fluorinated chemistries. And so this performance comes with a cost. But as I was saying earlier, this isn't how nature does this. Nature takes these not exotic or persistent chemistries, but through the careful organization of relatively simple building blocks. There's just not that many polymers out there. There's not biopolymers out there. There's a select few collection of materials, and they're just designed beautifully. And so one of the projects we're working on is a super hydrophobic textile coating. And we are looking at, and I think there's actually been a fair amount of work on this, but the key that I think is interesting at the Wyss is that we started it from an economic standpoint. It was, how does this scale? And it's not good to just get a paper out the door, but how can we self-assemble materials onto the fibers that are benign and then create a super hydrophobic textile coating? And then we can return those materials back to the natural system. And Bob's your uncle, we've replaced PFAS. Another thing that we can think about is the targeted fertilizer delivery. And then this gives us an idea of working within the system and recognizing where you're putting these things. Right now, we just dump an enormous amount of small nitrogen-containing compounds onto fields. They run off. They then do all kinds of things, creating dead zones in overgrowth and algae, and then dead zones in water. And it's because they're going to move. This is a moving system. And it's interesting to think about nature's targeted delivery of nitrogen. So nitrogen, there's soil microbes in bacteria, in soils, that will actually fix the nitrogen around the roots where it's needed. And so we had a company spin out from the Wyss Institute called Bio. And if you ever want to see a really beautiful scale up, this is a great place to go, because they have gone from, you can see them go from their little lab to their pilot scale to now manufacturing at Bio. And they've really focused on cell density, and it's just a beautiful example. And so what they've done is they've been able to scale up these soil microbes in a system that you can then apply to crops. And so I think the overall sense is that we aren't going to be able to build a sustainable future by exerting more control, but instead we need to think about designing materials that align with our living system. And that is the end of my soapbox. Thank you.